Hey everyone. So in this video, we're going to look at something called the scalar product of two vectors. This is also known as the dot product of two vectors. So you'll see those terminologies. Dot product is more of a slang term, and the reason it's called dot product is because to indicate that that's what you're going to do, you put a dot between the vectors. So let's say we have two vectors, vector A and vector B, and let's say that in component form, we have some value times I plus some value times j plus some value times k. And let's do the same thing with vector b. My apologies for the voice. It's coming back, but it's not all the way back yet. Okay, so we've got two vectors, a and b, defined as follows. And if we want to calculate the dot product of those two vectors, the way we indicate that we're doing that is we literally put a dot between the names of the vectors, so A dot B, or the scalar product of A and B. We simply multiply what we would kind of call the coefficients or scalars together. So A1 times B1, then we add A2 times B2, and then we add A3 times B3. That is the scalar product of A and B. So there are a couple of properties that we are going to investigate first to see if they are equivalent. The first one we're going to look at is the scalar product of uh, vectors commutative? Meaning, can you do them in either order, or does it make a difference? So that's the first one we're going to explore. We're not going to do all three all the way, but the first one we're going to do A dot B. So the first thing we're asked to do is we're asked to actually find the dot product. And then once we've found the dot product, we're going to see if we think that it suggests some sort of property, and then we'll prove that relationship if it does seem, in fact, like there is some relationship. So we're actually going to calculate the numerical value of the dot product. So we just take 2 times -1 plus 1 times 1 plus 3 times 1. So we did A1 times B1 plus A2 times B2 plus A3 times B3. And if we calculate that out, we get -2 plus 1 plus 3, we get 2. So let's now calculate B dot A. Technically, there is an order given. So if A dot B was A1 B1, then B dot A would be B1 A1. So you need B1 A1 plus B2 A2 plus B3 A3. But that'll just be -1 times 2, 1 times 1, plus 1 times 3. And of course, that's going to be the same thing. I'm going to -1 plus 1 plus 3, which is 2. So that's implying now that it's definitely possible that these are going to be commutative. Sometimes doing a simple example can help give us an idea if something might be true in all cases, because we can see the pattern happening. Well, the only difference is that these are multiplied in a different order. So yeah, it makes sense that this suggestion is that this suggests that A dot B is the same as B dot A. Well, how do we prove that? Well, when we're doing a proof, we do it with the generic versus specific numbers. So we're going to use these two. So if our proof needs to start it with us defining that. So let A, I'm just going to use these same ones from up here. A1I plus A2J plus A3K, and B is B1I plus B2J plus B3K. So now that I've got, my vectors established as like what they are, now I actually can figure out what A dot B would be. So that'll be A1 B1 plus A2B2 plus A3B3. But now we know that these are just numbers. A1, B1, and so on are just numbers. Numbers are commutative. Since numbers are commutative, we can switch each set of numbers. And now what we have is we have B dot A, because the B's are first now. So yep, we proved that A dot B is the same as B dot A. Or in other words, more formal words, the scalar product of A and B is equal to the scalar product of B and A. Okay, let's look at C and D. Remember that absolute value signs around a vector indicate that that is the vector's length. So if we want to find the length or magnitude of vector A and then square it, that's what we're doing first here. The magnitude of vector A squared. So I would simply do the magnitude of vector A, which is the square root of A1 squared plus B1 squared, sorry, A1 squared plus A2 squared plus A3 squared. So 2 squared plus 1 squared plus 3 squared. But then I'm supposed to be squaring that magnitude. So the square root and the square will just cancel. So I'll get 4 plus 1 plus 9. So I'll get 14. So the magnitude of A squared is simply 14. Okay, well, for D, I'm asked to do A dot A, the scalar product of A and A. So yes, you can have a scalar product of something with itself. So this would just be A1 plus A2 B2, A1 plus A2 plus A3. So 2 times 2, 1 times 1, and 3 times 3. And if we multiply those together, we get 4 plus 1 plus 9, which equals 14. So it does seem to suggest that these two things, the magnitude of vector A squared, would be the same as A dot A. That's our suggestion. So this suggests the magnitude of vector A squared is the same as A dot A. So we need to prove that. Um, so again, we need to start off by saying let vector A be A1I plus A2J plus A3K. We need to establish what vector A is. Once we've established what vector A is, we can either start with the magnitude and go this direction. I think I'm going to start with A dot A and show that it will equal the magnitude squared. So A dot A will be A1 plus A2 plus A3. But of course, that's A1 squared plus A2 squared plus A3 squared. Well, that's how we find the magnitude, but then we square that. So we basically have what we need. How do we more explicitly write that though? Well, we can say, well, if I square root that, that's the magnitude, but I need the magnitude squared. So notice I haven't changed the value of my statement. I've added a squared and a square root to compensate for one another. So that's going to be the magnitude of vector A squared. So you want to make sure you're not changing the value of something. So if I add the square root, I also have to add the squared so that I haven't done that. But that's exactly what I need to get it in the form of magnitude. Okay, E and F. We're not actually going to do this one, but yes, E and F are also equivalent, just due to time. So these are equivalent. I believe there's an exercise in your assignment that asks you to show this as well. We are going to be able to use all of these rules as we move forward. We know that it's commutative. We know that the magnitude of a vector squared is equal to the dot product of the vector to itself. And we can see that the distribution property also works here. That's basically what this is, right? So now that we have that, we're going to be able to use that moving forward. So Moving forward, let's talk about another way to define dot product or scalar product. One way to define a scalar product is the algebraic definition that we did up here. So I would call this the algebraic definition. But there's also a geometric definition of scalar product. And the geometric definition of scalar product is if you do A dot B, it's the magnitude of vector A times the magnitude of vector B times cosine theta. Theta is the angle between the vectors. It's the angle between vector A and vector B. So we have two definitions for this. Let's use the second definition now, the geometric one, in order to find the scalar product of vectors A and B. Okay, so if we want the scalar product of vectors A and B, we're using our geometric definition this time. Now, how do you know which definition? It depends on what they tell you. If they give you the magnitudes in an angle, you use the geometric definition. If they give it to you in either the vertical matrix form, basically any component form, then you're going to use the algebraic definition. Sometimes you'll even use both on the same problem, and we'll get to that. Okay, so rad 2 is the magnitude of vector A, 3 is the magnitude of vector B, and then we'll have cosine 45. So we'll have rad 2 times 3 times rad 2 over 2. So those rad 2's cancel with this 2, so I just get 3. So that is the value of the scalar product. What we haven't talked about yet is what does that answer mean? Like, does it mean something? It actually does. The value of this answer tells you what kind of angle is between the vectors. You're like, well, we already know what kind of angle is between the vectors. It's 45 degrees. But let's say we had done this with the algebraic definition and we had gotten 3. If the value of the dot product is positive, greater than 0, then the angle is acute. The angle between the vectors is acute. If you do B and you get a negative result, did we get a negative result anywhere up here? No. So positive result here, positive result here. So every angle we've worked with so far has been acute. But if that happens, you're probably anticipating theta is obtuse. Well, we've kind of got sort of 3 main categories of angles, right? We've got acute, we've got obtuse, and we've got exactly 90. That's going to happen if your dot product is equals 0. Theta is 90 degrees, or pi over 2 if we're in radians. Theta is 90 degrees. So another way of saying that would be that vector A is perpendicular to vector B. So that I think leads us into our next set of problems here. Our next problem. Here we go. I had to find another paper. So we've got these 2 definitions of dot product, right? We've got an algebraic definition of dot product, which you see on the left here. That's just a smudge, ignore that. And we've got the geometric definition of dot product on the right. Those 2 are equal. We are not going to do the proof of that. I use suit in my notes, but it takes a little bit of time, and these are video notes, so we want to keep them a little bit shorter. We can prove, using the law of cosines, actually, we can prove that those 2 things are actually equivalent in the same sort of general way that we proved that these vectors were commutative, the product is commutative, that this was true. In the same sort of way, we can prove that these 2 things are true, okay? So know that we can do the proof, we're just not going to due to time. So it can be useful to use both definitions at once, and they're equal to each other. So we end up getting this sort of expanded formula A1 B1 plus A2 B2 plus A3 B3 equals magnitude of A times magnitude of B cosine theta. Let's use that. And the most useful thing to do with that is to figure out what the angle between vectors is. So let's say they give you vector A and vector B, and they want you to figure out the angle between those vectors, correct to 3 sig figs. So if we think about in space, if we started these things at the same point, remember you can move vectors around. Vector A is going to point off in some direction. Vector B is going to point off in a different direction. Right now, I don't know if it's going to turn out acute or obtuse or what. Well, actually, I do know because I worked it out already. So maybe here's vector B, right? And we want to figure out the angle between them. We want to know that angle. That angle might be acute, it might be obtuse, we'll find out. So the first thing we need to do is we need to use our algebraic definition. So 2 times 3, -3. Oh, that's supposed to be a J, not a B. Typo. 2I minus 3J plus 2K. Typo. Okay, so 2 times 3, -3 times -5, and 2 times 1. Now on the other side, we're going to put the magnitude of each one of those multiplied times each other. So the magnitude of vector A will be 2 squared plus -3 squared plus 2 squared. The magnitude of vector B will be 3 squared plus -5 squared. Now you know the negatives are going to cancel, so if you want to just not worry about writing the negative, I'm cool with that. And then we have cosine theta. So we get this formula where everything is filled in except for the theta. So now our task is just to work out what this is. So if we add all this stuff together, we get 6 plus 15 plus 2, that equals 23. Here we get 4 plus 9 plus 4, that's going to be rad 17. Here we get 9 plus 25 plus 1, that's rad 35. Cosine theta, divide over the radical values. And now we just do cosine inverse. Typically, when we give our answers for this, we give them in degrees. If it says radians, do radians, but otherwise, let's use degrees. I'm going to make sure my mode is in degrees. It is. I've been doing work with algebra 2 trig, so we usually use degrees in there. Okay, so second cosine, inverse cosine 23 divided by rad 17 times rad 35. And I can just keep them under one radical together. That will not change anything. So we get about 19.5. 3 sig is what they've asked for. That is the angle between our vectors. That is probably um, the most useful way that you're going to see these problems is to find an angle between the vectors. Another thing that you might see is they might give you 2 vectors. It might be 2-dimensional problem or 3-dimensional, but they'll want you to figure out some sort of missing value so vectors are perpendicular. But remember that perpendicular vectors just have a dot product of 0. So we just need to do the dot product and set this equal to 0. So if I do t times 2 minus 3t, 2 minus 3t, plus t plus 2 times t, I should end up with 0. Why am I not using the geometric thing here? Well, because I don't really need that part of it. I really only need to use both of these if it says find the angle between. Here they give me that it's perpendicular, so I know the dot product is 0. So now I just work this out, and I'm going to do a little algebra to get to the value of t could be. So I'm going to get -3t squared. Let's just move it all to the other side. So we get +3t squared. Oh, and then plus t squared. So put those together and I'm getting negative t squared, but I'm moving everything over. And then minus 2t minus 2. So I'm going to get, oh, I'm missing, what did I just do? I did not add like terms correctly. I did wrong. I got a 2t and a 2t, 4t. Right, I didn't add like terms correctly. Also, see, I can factor out a 2t, so I get t plus 2. So that means t is either 0 or negative 2. Okay, so those would be the values of t that make those two vectors perpendicular. Oh, wait, not negative 2. Did I fail? Yep. By moving stuff over, I messed myself up again. And moving this all over to the other side, it should be a minus, and that should be a plus. My bad, I was trying to rush through the problem too quickly so that I can move on to our final example, which was they give us two vectors A and B, and they tell us that A plus B, these are vectors. These are not component forms. So vector A plus vector B put together and 2A minus B put together, those two vectors are perpendicular. Also, A minus B and 4A plus B, those two vectors are perpendicular as well. So how do I deal with that? Well, let's think about like what do we know about perpendicular vectors? We know that their dot product is zero. So let's start off by saying vector A plus B dotted with 2A minus B. When I do the dot product of those, I get 0. This is an important thing to remember from before. You can distribute, if you can distribute and maintain equality, that means you can FOIL and maintain equality. So I can FOIL this out. So I'm going to have 2 uh, vector A dot vector A minus vector A dot vector B plus 2 vector A vector B dot vector B minus vector B dot vector B. So I just distributed everything and I get 0. Well, how could I simplify this down a bit? I can, of course, add these two in the middle to get 1 vector A dot vector B. But I could also do stuff with this as well, because one of the things we just proved recently is that vector A dot vector A is the magnitude of A squared. That could be helpful for us. So we have 2 the magnitude of vector A squared plus vector A dot vector B minus the magnitude of vector B squared. Okay, so that's what I've got so far. I don't know that I can simplify that anymore. Let's look at the other one and see what happens. Okay, so vector A minus vector B dotted with 4A plus B. That has to equal 0. So same kind of thing. I'm going to multiply and FOIL this out. So I'm going to kind of combine steps a little bit. I know that if I do vector A dot vector A, I get the magnitude of vector A squared. So then I'm going to get plus vector A dot vector B minus 4 vector A dot vector B minus magnitude of vector B squared. Notice I'm also reordering everything so that A is first and B is second. So like here when I did vector B times vector 4A, because I know that vector dot product is commutative, I can switch that order and I know I'm not going to mess anything up. Okay, let's simplify this a little bit. We've got 4 magnitude vector A squared minus 3 A dot. Oops, not equals 0. I forgot my equals 0. Okay, so let's see, I simplified some stuff. So now I feel like I'm a little bit stuck because I feel like I've simplified as much as I can. Well, I know that I need to use these two together somehow, right? So I'm kind of thinking that maybe I'm going to need to use the scalar product at some point to find the angles. So I'm thinking the scalar product between A and B is going to be important. So maybe I'll put my work to that. I'm going to see how far I can get with that. And then we're going to kind of run into a problem and then we'll fix our problem. So the scalar product of A and B. Actually, I think I might not need. Notice we don't have any algebraic definition going on. We mostly have stuff that sort of represents the geometric one. So I think I'm actually going to not worry about writing it with this. Maybe I'll write the geometric one because I feel like that more sort of closely resembles the work I've already got. Okay, now what can I do here? It looks like I have vector A dot vector B here. So what if I got this alone and then substitute that stuff? Would that help? Let's try. So I've got vector A times vector B. Let's substitute that in. The problem is, though, I've still got too many variables. I need to solve for cosine theta, but I have still vector A and vector B going on in there. So I need to think of some other way to kind of relate some of these things together. And here's something I'm kind of noticing. I've got this relationship here, and then what if I got A dot B alone here? What would that look like if I got A dot B alone? Or what if I like compared their sizes? So let me get three vector A vector B alone. Okay. So now I know that three of these will equal one of these, right? Because it's three times as big. So I need three of these to equal one of these. Okay. So let's see. Is there a way I can maybe get one of those vectors alone, like either vector B alone or vector A alone? Yeah, let's do that. Because if I get vector A alone or vector B alone, either one, I can then substitute in here, and then maybe some stuff will simplify out. So then I'm going to get vector B alone. So I've got 3 vector B squared, and if I move that over, I'll have 4 vector B squared. And then I'll move the vector A squareds over. There are negative 6 of them, so if I move them over, I'll have positive 10. And then I'll just divide both sides by 4. So the magnitude of vector B squared is 10 fourths the magnitude of vector A squared, or in other words, 5 halves. Actually, maybe I'll leave it 10 fourths. Because then if I square root that, I'll get rad 10 over 2 magnitude of vector A. Okay, if I plug that in here now, I'll get magnitude of, uh, I'll get rad 10 over 2 squared. So that'll turn them back into 10 fourths magnitude of A squared minus 2 magnitude of A squared. Then over here, magnitude of a squared times rad 10 over 2 magnitude of a squared cosine theta. Every single term, every single term has a magnitude of a squared. Even this term, because it has two magnitudes of a multiplied. So those will cancel. So I'm going to get 10 fourths minus 2, which is going to be 2 fourths or 1/2, divided by rad 10 over 2 is cosine theta. We have a winner. Those magnitude of a squareds canceled. Now we can put that in our calculator and figure out what our angle is. These twos are going to cancel, so I'm going to have inverse cosine of 1 over rad 10, and we get 71.6. 3 sig figs because they didn't designate anything. Okay, long. This gives you a strategy. This is not how you're going to do every problem you see, but it gives you some options to think about. Notice that we used a lot of the rules from the previous example. We were able to distribute vectors because now that we know that dot product of vectors is distributive, we know that it's commutative. So like here, when I multiplied vector b times vector 4a, I didn't write it in that order because I knew I was allowed to switch them because it's commutative. And then I also, every time I had vector b times vector b, that turns into the magnitude of vector b squared. So I used all three of those rules we talked about on the front. But then I also use traditional algebra techniques like substitutions. So there's no like one way solves everything with these sometimes, but that's a strategy that you can kind of use, different things that you can think about doing. Okay, that is the end of this video. Thanks for watching.